Chapter 7, Cloud Computing and Remote Access, Part 2. In this second half of this week's lecture, we're going to take a closer look at a term that I've been throwing around throughout the entire course, encryption. But this time we're going to take a closer look and see what's actually going on with encryption. Without it, the internet wouldn't be what it is. Our ability to do any business, to conduct transactions online, wouldn't be there. It just wouldn't be possible. So encryption is a big deal to us. So what is it really? Well, encryption is the scrambling of information so that it can only be read by the intended recipient. It actually provides what's called the CIA triad: confidentiality, integrity, and availability. Confidentiality, which means keeping secrets secrets. Integrity, making sure that it's not changed. And availability, that it's available to whoever needs it when they need it. Encryption is performed with an encryption key. Now, this is one way we could look at it. This is actually a very simple form of encryption. This dates all the way back to the Roman Empire. And it's what's known as a substitution cipher. And we have some terms we need to look at. Our unencrypted message is called plain text, right here. And in this case, the plain text is simply our unencrypted alphabet, right? Ciphertext is the encrypted message in its encrypted form. So stay with me. And what I do is I have what's called a key. And in the case of this substitution cipher, here's the key. So in plain text, a letter A equals encrypted D. Plain text, letter H equals encrypted K. Q equals T. Z equals C, and so forth. So if I wanted to encrypt this message, here's my plain text message right here. And then I simply take every letter and I line it up with its ciphertext equivalent. So the T becomes a W. The R becomes a U, and so forth. When I'm done, I'm left with this string of ciphertext right here. And I can't really decrypt this. Well, I can. This is actually a game. It used to be in the Portland Press Herald years ago in the comic book section called Crypto Quip, where you were given a string of ciphertext and you had to figure it out. But stay with me. I can't really decrypt this without the key. So to decrypt the message, go to my ciphertext, find W, go up. Okay, that equals a T. There's my first letter of my message is a T. Second U decrypts to R, so my second letters are, and so forth. And you just go through this until you've decrypted the entire message. So how can I defeat this? Well, the little crypto quip example there is not very difficult. People can do it over breakfast, right? By the time they get done eating their cereal and toast. Modern encryptions are mathematical. They're mathematical constructs, and they're far more secure and far harder to brute force, which is the term which means just to try to figure it out, than a simple substitution cipher were. So it's not really doable. Although I can brute force some modern encryption techniques, really what you're trying to do though is you're trying to find the key. Right? Maybe I can get the key compromised. Maybe I can steal it from somewhere. Or maybe I'm going to sit there and try to go through every letter combination and figure out what works. We can encrypt in two primary ways. We have what's called private key encryption and public key encryption. Private key is this example right here. So I want to send this message. I have this key. I wrote the message. I took that message and I threw it in the mail and mailed it to you. You go to the mailbox, take it out. You take the same key and decrypt the message. Symmetrical. The keys are the same ones. That's where that symmetry comes in. Looks a lot like this in what we're talking about. right? I'm going to take this message, encrypt it with my private key, send you the message, and send you the key so you can decrypt it. Huh. What's wrong with that? Exactly. What about the key? If the key gets compromised while it's in transit, then all is lost. I'm not doing anything. Private key encryption can be extremely secure because I can use a really long, really complex mathematical key to encrypt my messages. And we're talking stuff that would take, if you tried to brute force it using modern computers, like a modern PC, you would take several thousand years to try to brute force it. There's just not enough time to go through all the possible combinations. It works really, really well, except for that issue of how do I get the key across. It's hard enough between an organization, let's say with an office in New York and an office in Paris. They're going to share keys, and they're sending communication back and forth across. There's no secure way of getting that key over there, other than putting it in a briefcase, handcuffing it to somebody, and sending them on an airplane all the way over. Part of security, though, is regularly changing my keys. That's one of the ways you protect against brute force attacks, is you just change the overall key at some point. Well, if I got to send a person on a plane every time I do that, that's not very efficient. And if I don't have just one branch office, if I got 50 branch offices, well, you can see it's not really very scalable. Shopping on the internet, forget about it. But then we have public key encryption. Public key encryption uses two keys, right? We have a private key that only the owner of that key has, and then a public key that anyone can get. It's publicly available. In fact, they're usually put out on public key servers. You can just go and get it. Together, they're known as a key pair. And they're mathematically tied together. And this makes a form of asymmetric encryption. In other words, the key that I use to encrypt my message cannot be used to decrypt it. So that's key. That's foundational to how this works. Let's take a look at it. So if I have an entity over here, there we go. We'll just do our generic drawing for a PC. And I'm sending a message over here, and I'm doing it using public keys. Well, each one of these systems, if you will, each one of these users has a public key. And a private key. And the same over here. Public key and a private. The private key is, as the name suggests, we have to keep that key secret. If you lose your private key, you're compromised. But my public key I share with everybody. So in this case, what we're going to do is we're going to exchange public keys. One goes here, and then one goes here. So now each of our systems has a copy of the other's public key. So I want to turn around and send a message from here to here. So here's my message. All right, there we go. That's the message. What I do is I'm going to encrypt it using this system's public key. It's going to go from plain text to ciphertext. And then I'm going to send that across the wire, right across the open internet, whatever, we don't care because it's encrypted. And when the ciphertext arrives, the user at this system, they use their private key to decrypt that message, to end back with the original plain text message. So the public key cannot be used for decryption. It can only be used for encryption in this case. If I want to send a reply back, the same thing goes on. I'm going to take this user's public key, encrypt the message, turn it to ciphertext, send it across, and then when it arrives, these users will take their private key and decrypt it. Back and forth, back and forth, back and forth. This solved that problem of how do you get the symmetric key around. You simply don't. I can send the public key wide open, it makes no difference, and I safeguard my private key. This is what led to the internet being what it is. Without this, we wouldn't have shopping. Probably ought to take a look at that, right? I love shopping. I always have something on order from Amazon. How do I know that what's going across Amazon is secure? How am I sending this? Well, I know it's secure because see, I got a little green padlock right there, and Chrome tells me it's secured. Great. How does Chrome know that it's secured? It does it through public keys, or more specifically, something we call a digital certificate. And we can look at digital certificates. Let's take a look at this. So right here, I'm on Amazon.com, and I went through Chrome's little security control panel. And if you can see, I have an option down here that says, view the certificate of this site. It's telling me everything's green. We're all secure. And there's a certificate. So let's take a look at it. So it tells us what the certificate is intended for. It's meant for proving our identity. It's issued to Amazon. It was issued by Symantec Class 3 Secure CA. CA stands for Certificate Authority. And it was good from end of October of 2016 all the way to the end of 2017. Okay. I look inside the certificate, and here's where we start getting the actual substance. Because inside this certificate is the public key. Scroll down, we can see some other information here. Our validity times, thumbprint things, all that kind of stuff. And right here, there it is. That is the public key in hex to Amazon. And it's a 2048-bit number. The public key, along with this other information, again becomes what's called a digital certificate. This is what's called PKI, Public Key Infrastructure. And it's why online commerce and online banking and everything else works. My browser trusts this website because this website has a certificate saying who it is. Well, okay, that's great, but how do I trust the website? How do I trust their certificate? It's through what's called a chain of trust, right? And we totally don't trust individual websites. You can go and make your own certificate at the Linux command line in like 20 seconds, right? A couple commands, and there you go. You have a public key, hand it out to everybody, and it doesn't mean anything because you just made it. How do we know that these public keys work? How do we know that these public certificates work? Well, because we don't give them to ourselves. They're given to us by an entity that we inherently trust. Let's see what that looks like. If you look over here at my certification path, I can see that the Amazon certificate is actually the third certificate down in this chain of certificates. The top one is from VeriSign. VeriSign is one of the high-level root certificate authorities that's trusted universally. Anything that VeriSign puts out, because they have a vetting process. You just can't go to VeriSign and go, hey, I'm over here on Bob's Computers. Issue me a certificate, please. You have to prove who you are. This is where this all comes down to the whole authentication thing. Well, after you've proven to them who you are, they issue a certificate. And because we trust VeriSign, anything issued by VeriSign, we trust you. And it can go down several layers, right? VeriSign didn't give the certificate directly to Amazon. VeriSign issued a certificate to Symantec Class 3 Secure Certificate Authority. So this is the entity that Amazon bought their certificate from, some Symantec CA. The Symantec CA got their certificate from VeriSign. Amazon gets their certificate from here, and because it was retrieved from a system that had a certificate from VeriSign, we trust the whole thing. And this is how digital certificates work for us. They're used for the encryption piece, and they're used to help identify who somebody really is. That's huge. I mean, if I'm going to my banking site, if I want to go to bankofamerica.com, I want to make sure that the website I'm at is really Bank of America. I don't want it to have some man-in-the-middle attack somewhere, and it's really some hacker who put up a website that looks just like it, and I put in my username and password. I get a little error message, sorry, the website's down today, try again later, and meanwhile that person has my username and password. They're going to log into the real thing and steal all my money. Thank you very little. The digital certificates prove who these entities are. And when we see green, green is good. We have other kinds of encryption also, other ways of securing our transmission. And one way is called IPsec, Internet Protocol Security. And this is a protocol that is really used to, it's just an encryption protocol. There are many of them out there. This is just a very common one. And I can do this primarily through Windows machines. There's actually roles built into Windows Server that do this IPsec stuff. And it can provide an extremely secure connection between two systems. Another method, probably the one we're most familiar with, is SSL, Secure Socket Layers. This is that encrypted tunnel by which we look at our public websites. Right? If I go back over here and take a look at Amazon, look at my URL up here, HTTPS. The S means it's a secure socket layer. This is HTTP, the Hypertext Transport Protocol, going through an SSL tunnel, hence HTTPS. We can also use SSL to create VPNs, and this is the type of VPN you use to connect to the CSEC. That Cisco Secure Connect client, it's an SSL VPN. So my tunnel, in this case, is actually a secure sockets layer tunnel. Secure shell, we saw this in the previous lecture, in part 1. This is where I can get a terminal into a remote system, but do it securely. Secure Shell is actually a collection of protocols, it's several of them, that allow me to have an authenticated, secure tunnel to a command line environment. We most commonly use this for connecting with Unix or Linux systems. And I know that I'm talking to the real one because it uses certificates. Part of the SSH suite of software, if you will, suite of programs, is SFTP, Secure File Transfer Protocol. We don't see a lot of FTP around anymore, although it's still out there. File Transfer Protocol, it's simply a protocol that's optimized for moving files from location A to location B. It was back in the day, it's how we did a lot of downloads. Well, FTP inherently is unsecure. There's no security. Everything goes across in plain text, including usernames and passwords. SFTP is not FTP. I can do FTP through a secure socket layer. That's called FTPS. SFTP is simply part of the Secure Shell suite that looks like FTP. It behaves the same way. but it's not. And we can tell that by the port number. FTP uses ports 20 and 21. SFTP, along with Secure Shell, uses ports 22. You just went and downloaded something on the internet. You downloaded some program. You downloaded some map for some game or something. How do you know that that data, that program, hasn't been changed on the way down? How do I know that somebody didn't get onto that server and replace the innocent real product with a piece of malware? Or if I had a man-in-the-middle attack coming in and somebody intercepted my transmission and sent me what I thought was the original program, has the same name, but it's a piece of malware. Well, I could use something called a hash. Hashes are algorithms that allow me to prove that my data hasn't changed any. And it's a mathematical thing, and again, it is really hard math, that whole math thing. But I take a file, and what I do is I'll run a hashing algorithm against it. That's worth taking a closer look at. Let's go ahead and clear this out. Okay, so I have a file over here. And this is out in the internet somewhere. And what I want to do is I want to download it over here, right? To make sure that this file hasn't been altered, what we might do is use a hashing mechanism. So the publisher of this file will publish the file, and then they will run a hash against it. And this hashing algorithm produces a hash value. And I'm just going to draw it down here as like a long box, right? It's gibberish to us. It's just a bunch of letters and numbers, and they can be pretty long. The point is, that hashing algorithm does a bit-by-bit analysis of this file. And the combinations of the hash, the letters and the numbers, are only from this data. If I was to change one bit of data inside this file, my hash value changes. So what I do is, on my website, I put both the file to be downloaded and the hash, is called a checksum. And over here, when a person wants to download it, you download the file, pull it down, download the checksum, pull it down, and then I run the same hashing algorithm over here on the downloaded file. I'll take that checksum and compare it to the one that I downloaded from the site. They should be identical. If they are, it means the data has not been altered. If they're not, warning, something's wrong, something's not right. There's two hashing algorithms we need to be aware of. One is called MD5, Message Digest 5, and SHA. MD5 is an older algorithm, and because it's older, it's not as secure as SHA is. And I can do all kinds of tweaks to this SHA-1, SHA-3, SHA-256. I can change the level of the hash that's being done to make it harder to spoof, to make it harder to fake. Both are still in use. You'll still see MD5 out there. A lot of times, though, it's used in conjunction with SHA. And that wraps up our second half of this week's lectures. As always, if you have any questions, please reach out to me, and I'll see you next week.